Section 3 focuses on long-term climate and development futures. So essentially it's looking at long-term climate change impacts and related risks. Future warming will be driven by future emissions and will affect all major climate system components, with every region experiencing multiple and co-occurring changes. Many climate-related risks are assessed to be higher than in previous assessments, and projected long-term impacts are up to multiple times higher than currently observed. Multiple climatic and non-climatic risks will interact, resulting in compounding and cascading risks across sectors and regions. Sea level rise as well as other irreversible changes will continue for thousands of years at rates depending on future emissions, and we can say this with high confidence. Again, we have seen some of these things. With every increment of global warming, regional changes in mean climate and extremes become more widespread and pronounced. I split this figure into multiple pieces. So we are looking here at global warming level above the baseline of 1850 to 1900, and reminding ourselves that 2011 to 2020 was around 1.1 degrees C warmer than 1850 to 1900 baseline. We are looking at world at 1.5 degrees C here, at 2 degrees C here, and this is the least time global surface temperature was sustained at or above 2.5 degrees C was over 3 million years ago. So 3 million years ago the Earth did reach 2.5 degrees C above the baseline. Here is world at 3 degrees C and at 4 degrees C, and we are looking at various things like annual hottest day temperature change in degrees, and you can see the uneven distribution. The other thing we should remember again is that these models are good at doing temperature projections or future simulations given the RCPs or SSPs and the combination of them at regional scales. If you go to very local scales, the uncertainties increase. But what is not in doubt at all is that as the global mean temperature or global warming levels go up, more and more regions begin to get tremendously hot. Annual hottest day temperature is projected to increase most 1.5 to 2 times the global warming level in some mid-latitude and semi-arid regions, and in the South American monsoon region here. And the Middle East, Mediterranean and Sahara are already warming quite fast, having all sorts of impact on the monsoon circulations, for example. And urbanization further intensifies heat extremes as well as you go to higher temperatures. There are also discussions about dew point temperatures. So as temperatures increase, humidity levels in the atmosphere increase, and human tolerance for heat depends on humidity levels, because the body can begin to lose its ability to sweat in hot temperatures as humidity increases. Looking at annual mean total column soil moisture change, again 1.5 to 3 and 4 degrees. Projections of annual mean soil moisture largely follow projections in annual mean precipitation, but also show some differences due to the influence of evapotranspiration. Obviously the uncertainties begin to build because models' abilities to do precipitation simulations are always quite deficit for compared during historical periods, and then you add evapotranspiration, which is vegetation, so future projections of vegetation also add uncertainties. But nonetheless, here we are in terms of the change. So this is soil moisture being positive wherever rainfall increases, and being negative wherever rainfall tends to decrease. So the heat and the soil moisture go together here in the Amazon, for example, and Sahel gets more rain. India monsoon is expected to recover, but this of course has all kinds of issues in terms of how the models do in the historic period, where monsoon has actually trended down on the seasonal mean, but most models don't capture that. But again, as warming increases, the Amazon gets really worse and worse with temperature and correspondingly precipitation and soil moisture. So you can see Sahel gets more and more, and there are already some claims being made that desert regions will become more green. Small absolute change may appear large as percentage or sigma changes in dry regions. So you have to remember that the standardization depends on the local sigma, which can make the signal amplified in dry regions. Annual wettest day precipitation change, again percentage change being positive in the regions where soil moisture shows positive change, being negative where the soil moisture shows negative change. So you can see that the rainfall drop is not as high as the soil moisture drop, and that's because of the combination of temperatures. For example, temperatures in the Amazonia get hotter and hotter, even though rainfall decreasing is not as serious as the soil moisture drop here in sigmas, 1.5 standard deviations. There are model deficiencies also in the ITCZ region over the ocean and so on, so one has to keep all those things in mind. But in general, it's fair to assume that precipitation projections tend to be less reliable than temperature changes. Future climate change is projected to increase the severity of impacts across natural and human systems and will increase regional differences. Examples of impact without additional adaptation: so risk of species losses, percentage of animal species and seagrasses exposed to potentially dangerous temperature conditions. So you can see on land and water there are many regions which get more and more exposed to extreme temperature conditions. Marine heat waves is a big discussion now. So with increasing global warming levels, larger and larger regions, especially those that are already warm in the climatology, like the Indo-Pacific warm pool, the Coral Triangle here, the Sahel band here, and so on, Australia, Northwest Australia, etc., get fairly seriously affected with rising global warming levels. Projected temperature conditions above the estimated historic 1850 to 2005 maximum mean annual temperature experienced by each species, assuming no species relocation. As temperatures change, many species tend to move, especially in the ecosystem. There are so-called general mobilists or mobile generalists, and sedentary specialists. So ecosystems don't move, individual species can move, and it's the same for marine species as well, whereas here the assumption is that species are now not relocating, and that's how the exposure to additional heat is computed here. Okay, so that seems fairly obvious as well. If you look at heat humidity risks to human health, which is the dew point temperature I just mentioned, you look at the historical base period 1991 to 2005, days per year where the combined temperature and humidity conditions pose a risk of mortality to individuals. So what is the human tolerance? There are some details here. So there's still some debate, because when a heat wave hits in Europe, mid-latitudes, thousands of people die. Mortality in the global south tends to be much lower, presumably because people have adopted over time. I have a strong breeze here. I live without an AC, as you remember, so I like to keep the windows. It's not completely open, but it's still plenty of wind coming through, which is nice, but it leaves a little bit of a hissing sound in the recording. Apologies for that. So here the number of days up to a year, and you can see that the Southeast Asian Indonesian Seas Maritime Continent region is pretty bad already at 1.7 to 2.3 degrees centigrade warming levels, and it gets worse as temperatures increase, but you get a lot of other regions having more and more warm days. So projected regional impacts utilize a global threshold beyond which daily mean surface temperatures and relative humidity may induce hyperthermia that poses a risk of mortality. The ability to sweat away the heat becomes severely limited. The duration and intensity of heat waves are not presented here. Heat-related health outcomes vary by location and are highly moderated by socioeconomic, occupational, and other non-climatic determinants of individual health and socioeconomic vulnerability. The threshold used in these maps is based on a single study that synthesized data from 783 cases to determine the relationship between heat humidity conditions and mortality, drawn largely from observations in temperate climates. So that may not be so totally applicable to the global south. Food production impact, maize yields as a percentage change in yield. You can see the negative numbers. There are few positive numbers, but with uncertainties or low confidence. So 1.6 to 2.4 degrees C and 3.9 to 6 degrees C. You can see large regions, the bread basket of the US, the bread basket of North India, and large parts of China and Southeast Asia begin to lose crop yields by fairly significant amounts as the global warming levels go up. Similarly, fisheries yields, you can see 0.9 to 2 degrees C warming and 3.4 to 5.2 degrees C. Changes in percentage in maximum catch potential. There are a lot of areas with little or no production, and they are not assessed here, but there are areas with model disagreements over here in the Arctic, Mediterranean, and Southern Ocean, the southern part of western coast of South America, and so on and so forth. In general, I would say the uncertainties begin to grow with these, because these are empirically derived relations in terms of catch potential, and the details matter. Here, projected regional impacts reflect fisheries and marine ecosystem responses to ocean physical and biogeochemical conditions such as temperature, oxygen level, net primary production, etc. Models do not present changes in fishing activities and some extreme climatic conditions. Projected changes in the Arctic regions have low confidence due to uncertainties associated with modeling multiple interacting drivers and ecosystem responses. So take these with a pinch of salt, as you would. Risks are increasing with every increment in warning, so reasons for concerns here again. High risks are now assessed to occur at lower global warming levels. Global surface temperature change relative to 1850 to 1900 here, historical period coming out, and then heading to various scenarios and the benign scenarios down here. 2011 to 2020 again was around 1.1 degrees C warmer than the base period. Global reasons for concerns, which we have looked at in AR5 versus AR6. So here again you have confidence levels and the transition range from undetectable to very high. So you have AR5 and AR6. You can see that very quickly the new assessment is hitting fairly high risk levels from 1 degree C to 2 degree C. Here you had moderate ranges going well past 1 degree C, whereas here below 1 degree C for unique and threatened systems you are hitting high risks. Similarly, almost all of them here you had basically high risk going all the way. Here you hit very high risk very quickly by 2 degree centigrade warming, although the confidence level is not high here, but confidence level is high, just above 1 degree C, and so on. This is for extreme weather events. Distribution of impacts, global average impacts, and large scale singular events. Again, people debate about tipping points, large scale singular events, and so on, whether these are heuristically argued or whether models can reliably resolve them and represent them, and so on and so forth. Nonetheless, it all comes down to how we deal with risks. These are risks, and there are of course perceptions, and vulnerabilities matter, and whether you have the ability to even prepare for them matters, and so on. Risks also differ by system. So you have land-based system, ocean, coastal ecosystems. Similarly as before, you're looking at wildfire damage, permafrost degradation, biodiversity loss, dryland water losses, tree mortality, carbon loss, and so on. And for coastal and ocean ecosystems, you have warm water corals, kelp forests, seagrass meadows, epipelagic rocky shores, salt marshes, and again these amber scales going from low to very high with various levels of confidence shown with dots on the side. I have several podcasts talking about corals which are responding fairly well to warming in the ocean based on their ability to find the symbiotic algae that are tolerant to high temperatures. There are adaptation choices and there are genetic abilities to do this. So this biological responses to global warming is a bit tricky, so one has to always watch out to see how reliable we are in depicting these future risks. Risks to coastal geographies increase with sea level rise and depend on responses. So this is why now response is included in the risk. Hazard, vulnerability, exposure, and response now constitute together the actual risk. Global mean sea level rise projected, it goes up to 1 meter in the worst case scenario, but half a meter even in the best of scenarios by 2100. And this is irreversible in the sense, even if we keep the global warming to its limits, the glaciers that have melted, the steric rise that has happened will not revert very easily or very quickly, or very quickly. So looking here at risks assessed with medium confidence, so small r is no to moderate response and R is maximum potential response. So if you have maximum potential response with sea level rise, you reduce the risk, whereas with moderate or no response, you hit higher risks very quickly in urban atoll islands, in Arctic communities, large tropical agricultural deltas, and resource-rich coastal cities. You can see that maximum potential response here can delay the actual risk quite a bit, up to 1 meter sea level rise. There are many practical details. For example, can a community really prepare for a 1 meter sea level rise, or will it be determined completely by how much it costs? Right now it turns out that most communities decide how much to protect against in terms of sea level rise. Basically depends on how much it costs. So the uncertainties in sea level rise may not matter as much as we think, because there are lots of uncertainties in sea level rise, because they don't consider land movements and glacier melts and so on. Adaptation and socioeconomic pathways affect levels of climate change. So limited adaptation, failure to proactively adapt, low investment in health systems, etc. Incomplete adaptation, as in incomplete adaptation planning. Moderate investment in health systems. Proactive adaptation, where adaptation management is proactive and higher investments in health systems are made. You can see heat-related morbidity and mortality. With proactive adaptation, more warming levels are tolerated and lower risks are created. With food security, food insecurity in terms of availability and access, again, SSP1, which is a very benign scenario, SSP3 is somewhat heading towards middle of the road. So you have high risks here, but challenges to adaptation increase in this direction. So you need much more adaptation to reduce the risks of food insecurity in terms of availability and access, for example. The SSP1 pathway illustrates a world with low population growth, high income and reduced inequalities, food produced in low greenhouse gas emission systems, effective land use regulation and high adaptive capacity, that is low challenges to adaptation. SSP3 pathway has the opposite trends. Okay. Examples of key risks in different regions. Absence of risk diagrams does not imply absence of risks within a region. The development of synthetic diagrams for small islands, Asia and Central and South America, was limited due to the paucity of adequately downscaled climate projections. To make risk calculations at regional levels, you need to have projected climate information at those scales, which require some downscaling efforts. With uncertainty in the direction of change, the diversity of climatologies and socioeconomic contexts across countries within a region, and the resulting few numbers of impact and risk projections for different warming levels make it difficult to represent risk levels in some regions. So without going into too much detail, again, you are looking here at risks listed are all of at least medium confidence level here, with some high confidence with 3 dots, and various warming levels. So you're looking at small islands, North America as examples. So you're looking at food production from crops, fisheries and livestock in Africa, biodiversity and ecosystems in Africa, mortality and morbidity from heat and infectious diseases in Africa, delayed impacts of sea level rise in the Mediterranean, water quality and availability in the Mediterranean, health and well-being in the Mediterranean, water scarcity to people in southeastern Europe, coastal flooding to people and infrastructure in Europe, heat stress, mortality and morbidity to people in Europe. And there are various details here like loss of terrestrial, marine and coastal biodiversity and ecosystem services, risks to water security in almost every small island. So you're in the middle of the ocean surrounded by water, but fresh water is a serious issue. Climate sensitive mental health outcomes in North America, human mortality and morbidity due to increasing average temperature, weather and climate extremes, and compound climate hazards. Okay, so these are serious issues. Okay, let's leave this for the next podcast in terms of long-term adaptation options and limits, because this one is already 20 minutes long. So I'm again giving a very brief introduction to the report, the synthesis, but the synthesis report is available online. You can definitely go and read it up if you are interested in more details. Okay.